Hello, everyone, and welcome to today's webinar. The topic of today's webinar is age-related changes in the human musculoskeletal system, a modeling-based approach. My name is Devyax Chander, and I work as a sales engineer here at Anybody Technology. Today, I will be the host of this webinar, and I'll be joined by my colleague, Christopher Iverson, during the Q&A session in the end. In the Anybody webcast series, we host a variety of presenters who have used Anybody modeling system in different applications. In today's webcast, I am very pleased to introduce our presenter, Professor Katarzyna Nowakowska-Lipiec from Silesian University of Technology. Katarzyna will present her recent work related changes in the human musculoskeletal system and demonstrate how musculoskeletal modeling can be used to simulate the effects of strength decline across the lifespan. Katarzyna's research is already published in the Journal of Clinical Medicine, and you can go and check out the paper if you would. The presentation will start in a few minutes or so. Just before we start, I will give a general introduction and overview of Anybody modeling system for those of you who are unfamiliar with the software or musculoskeletal modeling and simulations in general. First of all, I would like to draw your attention to the control panel. The control panel appears on the top right side of your screen. You're welcome to submit questions and comments via the questions panel during the presentation, and we will try to address the questions at the end of this webinar. In case we do not get to answer all your questions, we will try to do so by email within a reasonable time. So let's begin by having a look at what Anybody modeling system actually is. Anybody modeling system is a software that allows you to do musculoskeletal modeling and simulations. As input, it takes motion data and forces, and as output, it calculates internal body loads such as joint reaction forces, muscle activity, and metabolic energy. Anybody is used in a wide variety of areas and applications, and a few examples of these are movement analysis, product design optimization, sports optimization, orthopedics and rehabilitation, ergonomics with and without assistive devices such as exoskeletons, and in the automotive industry. The typical workflow in Anybody could look like this. You provide the recorded motion data as input and use the body models which you or others have built. And then you can optionally provide some kind of environment, which could be a special type of equipment or, for example, an exoskeleton. Then you can use Anybody to combine these things and run the inverse dynamics simulation, which solves the muscle recruitment problem. This basically means that we go from motion to calculating the internal body loads and the interaction with the environment in some cases. You can then output the results and use it for post-processing with, for example, some kind of finite element tool, but many users also close the loop completely by doing some kind of design optimization and then run the cycle multiple times. This actually brings me to the end of the introduction, and I will hand over the word and presenter role to Katarzyna instead.
Good afternoon. Hello, everyone. My name is Katarzyna Nowakowska-Lipiec, and I represent the Department of Biomechatronics, Faculty of Biomedical Engineering, Silesian of University of Technology in Poland. It's really pleasure to me to present my work during this webcast. The title of my presentation is Age-related changes in the human musculoskeletal system, a modeling-based approach. And in this presentation, I will show you how musculoskeletal modeling, particularly using an embodied modeling system, can help us investigate aging-related biomechanical changes that are difficult to assess experimentally, including, of course, internal joint loading, mass activity, and fatigue related indicators. Some word of introduction. So population aging is one of the major demographic challenges worldwide. The number of older adults is increasing rapidly, and by 2050 it's expected to reach more than 1.6 billion globally. This trend has important implications for healthcare, rehabilitation, biomedical engineering, because maintaining physical function and independence becomes one of the most important goals in older population. To understand these functional changes, we first need to look at the musculoskeletal system, which is directly responsible for movement, posture, and daily activities. Aging of the musculoskeletal system is associated with structural and some functional decline. And two important concepts are sarcopenia and dynapenia. Sarcopenia, which refers the loss of muscle mass, and dynapenia, which describes the decline in muscle strength and functional capacity. These changes affect mobility, balance, postural control, and may increase risk of falls, reduce independence, lower quality of life. But at the same time, our body often develops some compensatory postural and movement strategies. And while this adaptation may help us to maintain function, they also may modify internal joint loadings and can lead to some musculoskeletal pain. This is why in aging research, it's really important not only to observe movement externally, but also to try to understand what happened inside, what happened in musculoskeletal system. And this led us directly for biomechanical musculoskeletal modeling, which allow us to estimate these loads, to estimate internal loads, mass forces, which we cannot measure directly in vivo research. And why biomechanical modeling in aging research? So experimental data such as kinematics, ground reaction forces, and some anthropometry described mainly external movement characteristics. However, these age-related changes in posture, in movement strategy, and in the muscle function may strongly influence internal biomechanics. So we can use modeling as tools to move from external movement data to internal biomechanical insight, to estimate joint loading, mass forces, fatigue-related indicators. In the next part of my presentation, I will show you two complementary modeling-based approaches, which are used to investigate aging-related musculoskeletal changes. The first part combines experimental gait analysis with musculoskeletal simulation to evaluate internal knee joint loading during walking according to age, sex, and physical activity. And the second part is fully simulation-based approach focused on the dynapenia, healthy aging, sarcopenia, muscle activity, and fatigue during upright standing. So I will start with the first experimental driven modeling approach, focused on internal knee joint loading during walking. So this part of presentation is based on the results obtained with our collaboration with the University of Ostrava in context of two projects, LERCO and FORHAI projects. This study focuses on internal knee joint loading during walking. And then the aim of this cohort cross-sectional study was to assess differences in internal knee joint loadings during walking according to age, sex, and physical activity level using musculoskeletal modeling. And the study included 200 participants divided into 5 age groups with subgroups balanced by sex and physical activity level. Because we have inactive participants and also runners. Experimental gait data were collected at Human Motion Diagnostic Center at the University of Ostrava using Qualisys motion capture system. And this lower limbs kinematics and ground reaction forces was used as input data for musculoskeletal simulation in any body modeling system. And this allows us to estimate knee joint loadings during walking. Here we use gait full body model from antibody model respiratory, which represent the human musculoskeletal system, with 68 rigid body segment, more than 1,000 muscle actuators. but the upper limbs was excluded due to the missing kinematic data. And the model was driven by motion capture data, ground reaction forces, and basic anthropometric parameters such as body height and body weight. And the model was scaled individually for each participant using scaling length mass fed algorithm. And the simulation were performed into 2 stages. The first, a static standing trial was used for model scaling and parameter identification, and then the dynamic walking simulation. And musculoskeletal loads were estimated using inverse dynamics and with static optimization. And we performed 6 walking trials for each participant. So in total, we were performed 1,200 walking simulations. We analyzed knee joint reaction force normalized to body weight. And the results. So here we compare the youngest and the oldest inactive participants. And the upper plots show the resultant knee joint reaction forces during gait, during walking, while the lower plots present statistical parametric mapping analysis. In female, the older groups show lower knee joint loadings during terminal stance of gait, and in men we observe opposite patterns. So higher loading in the older group, around 45 to 50% of gait cycle. Also significant differences were presented during the swing phase in both sexes, male and females. Here we show the same comparison, but for runners. In what is interesting in female runners, age-related differences were less pronounced during stance, but also we observed some significant differences in selected parts of swing phase. In male runners, older participants show higher knee joint loading during part of stand phase, and also significant differences during swing phase. Okay. The obtained results indicate that age-related changes in knee joint loading during walking are phase-dependent and are differ between sexes and between activity groups. Also, we try to analyze the effect of physical activity on knee joint loadings. And the statistical parametric mapping analysis results show that physically inactive individuals exhibit higher knee joint loadings, especially in mid-stand phase, so around 40 to 50% of gait side. So in time when joint loads are the highest. In contrast, physically active individuals tend to show lower and more stable loading patterns. And the results demonstrated that age, sex, and physical activity level are associated with internal knee joint loadings during walking. And older adults, especially older females, generally showed lower loading value normalized relative to body weight. And what's important, regular physical activity was associated with reduced knee joint loadings. Future direction for further analysis will focus on more detailed analysis of force components, also loadings in other lower limb joints and muscle forces pattern obtained from musculoskeletal simulations. Another direction of our ongoing work also is prospective study, association between aging and knee joint loading during gait, during walking. We are currently performing musculoskeletal simulation for 60 participants who were assessed at baseline wave 1, and again after 5 years, wave 2. So in this work, we would like to evaluate the longitudinal changes in knee joint loading during gait, and to compare these changes between inactive individuals and runners. And the second part of presentation, how I said, will be connected with fully simulation-based analysis, fully simulation-based approaches. And the first study is from the dynapenia to healthy aging and biomechanical modeling-based analysis of muscle activity and fatigue. The aim of this study was to evaluate how age-related decline in muscle strength affect total mass activity, mass fatigue during upright standing across the 20, 50, and 80 strength percentiles in male and females, of course, using mathematical modeling in any body modeling system. And this part focused on biomechanical consequences of age-related decline in muscle strength. The muscle strength was scaled using hand grip data from Tompkinson et al. Hand grip norms obtained for 2.4 million adults aged from 20 to 100 years, and I analyzed 3 strength percentiles: P20, which represent a dynapenic strength profile; P50, which represent the population reference; and P80, which represents healthy aging profile. And this simulation were performed in an body modeling system using whole body standing model with predicted ground reaction forces, separately for males and females age groups across the different age groups, and obtain results. So model total muscle activity increases with age in both males and females, and this increase was relatively small until mid-adulthood, but became more pronounced after approximately 60 years of age. And the highest relative increase was observed in P20 group, which represent the dynapenic strength profile, and although females showed lower absolute total mass activity value, and the overall age-related pattern was similar across sexes. And piecewise regression showed a clear breakpoint after which total mass activity increased much faster, and this acceleration was strongest in P20 male group, which suggests that reduced strength capacity strongly increases muscular demand in late life. And these plots present the model-based muscle fatigue index, which reflects the optimization cost of maintaining upright standing. And the fatigue value remain also low until around 60 years of age, and then rise markedly, especially in P20 group, which represents dynapenic profile. This suggests that dynapenic strength profile require greater relative muscular effort to maintain upright standing. In conclusion, both total mass activity and muscle fatigue increase nonlinearly with age, with clear acceleration after approximately 60 years. And the highest model demand were observed in a P20 dynapenic profile, indicating that reduced strength capacity increases the muscular cost of maintaining upright standing. So this finding suggests that dynapenia may contribute to lower mechanical efficiency and higher fatigue especially in older adults. And the second study in this fully simulation-based approach is progressive loss of muscle strength, the effect of aging and sarcopenia on muscle function in older female. And in this work, we analyze how age-related muscle strength loss and sarcopenia may influence muscle function during upright standing also. And this study combined experimental assessment with musculoskeletal modeling to investigate the changes associated with reduced strength capacity, and the more detailed results and methodology you can find in the publication presented on the right side on this slide. And this slide presents the overall modeling workflow, the research process. So first, we perform clinical DEXA and postural assessment in older females group with and without sarcopenia. In second stage, we developed theoretical models of age-related muscle strength decline based on literature data, including both natural aging and progressive sarcopenia scenarios. And next, this strength reduction were implemented into an body modeling system to simulate the effect on total muscle activity and muscle fatigue during upright standing. And finally, in fourth stage, we additionally incorporated this experimentally measured posture data into the simulation, allowing us to investigate how both, so posture and also strength decline, may influence muscular demands in older adults, in older females here. And the study involved 20 older females classified into sarcopenic and non-sarcopenic groups based on DEXA assessment. We also evaluated sagittal standing posture using a Zebri's system, including trunk inclination and pelvis tilt. And this measurement were then used, how I said, as input data for musculoskeletal simulation in any body modeling system. In this part of the study, we developed theoretical models of age-related muscle strength decline associated with both natural aging and sarcopenia. The modeling assumptions were based on literature data, literature articles, particularly hand grip strength changes reported in previous studies. And two simulation variants were considered. The first, which represent natural aging with gradual decline in muscle strength over time. And the second represent progressive sarcopenia, assuming substantially faster reduction in muscle strength, especially in older age. And as shown in this graph, the difference between these two scenarios became increasingly pronounced with age. So this strength reduction profile were then implemented into an body modeling system to assess, to evaluate the influence on total muscle activity and fatigue during standing. All simulations were performed using whole body standing model with predicted ground reaction forces. We analyzed three different simulation variants. The first, which represented natural age-related muscle strength decline. The second, which simulates progressive sarcopenia with accelerated strength loss. And the third variant, which additionally incorporated age-related postural changes together with muscle weakness. And muscle strength decline was modeled at 5 years intervals between 50 to 90 years of age. And the main outcome, so we analyze also, like in previous study, the total mass activity, muscle fatigue, and additionally muscle activity of some selected postural muscles. And at this slide, I presented the results total mass activity of all muscles for analyzed simulation invariant natural aging and progressive sarcopenia. And the differences became particularly pronounced after around 60 years of age, indicating higher muscular demand associated with accelerated strength loss. At 65 years, the differences between these two variants, natural aging and sarcopenia, was approximately 14%, while by 80 years, it's increased to around 45%. So this suggests that sarcopenia may considerably amplify the biomechanical cost of maintaining posture in older adults. When we analyze some selected postural muscles, the same general pattern we observed. So muscle activity increased with age, but this increase was clearly greater in progressive sarcopenia model. And the greatest changes were observed in muscles which were involved in mating upright posture. So multifidus, semispinalis, erector spinae, and transverse abdominis. This suggests that accelerated strength loss changed not only total muscular demand, but also distribution of activity across individual postural muscles. And muscle fatigue for analyzed simulation in these two variants, natural aging and progressive sarcopenia. Muscle fatigue increased with age in both the simulation variants, but much more rapidly in this progressive sarcopenia model. After around 65, 70 years of age, this increase became strongly accelerated. And by 89 to 90 years, modeled fatigues in sarcopenia scenario was approximately 3 to 4 times higher than in natural aging. So these findings also suggest that progressive strength loss in progressive sarcopenia may dramatically increase the muscular cost of maintaining upright standing, especially in older adults. And the final stage of this study, in which we combine age-related muscle strength loss with experimentally measured postural changes in older women. So we put the obtained average value of trunk, tilt, and pelvis alignment into the model for these two variants, progressive sarcopenia and natural aging. And the results showed that model which incorporating progressive sarcopenia and altered posture demonstrated higher total mass activity and muscle fatigue compared to natural aging model. So the greater trunk inclination and pelvic alignment, pelvic tilt, changes which we observed in sarcopenia group were associated with increased muscular demands during standing. So these findings suggest that posture-related compensation may additionally amplify the biomechanical consequences of muscle weakness in older adults. In summary, both aging and sarcopenia increase the muscle activity and muscle fatigue during standing, and the effect became particularly more pronounced after around 60-65 years of age. And progressive sarcopenia substantially amplified the muscular cost of maintaining posture, especially in late life. And future perspective in modeling musculoskeletal aging. So Musculoskeletal modeling is a powerful tool for estimating internal biomechanical quantities and internal loadings that we cannot measure directly in vivo. And the next step in aging research is to further personalize these models by integrating the strength measurement, muscle mass, body composition, and maybe some functional phenotype data. This may help us better distinguish healthy aging from dynapenia, from sarcopenia, and move towards more physiology-informed simulation of older adults. I believe that this integrated and experimental assessment with musculoskeletal modeling may help us better understand functional decline associated with aging. Thank you for your attention.
Yeah, thank you very much, Katarzyna, for this excellent presentation. So just before we go to the Q&A session, I'd like to say a few words. First of all, I'd like to say that we recently released Anybody Modeling System version 8.2, and we're very excited to share a couple of features about it. So there's a whole new user interface that you can now preview with the Anybody Studio, and it's a completely different look and feel to the software. And on a more technical side, there's also some improvements in mocap data handling. So, for example, we now have the ability to read C3D files with rotation data, and that enables the processing of mocap data collected from markerless system. So, but apart from that, I'll just say a little bit more about our online resources and some upcoming events. So if you want to know more about Anybody technology, you can check out our website, anybodytech.com, where you can find different events, special dates, and previous webcasts. You can also check out anyscript.org, which is our community website for people using Anybody. Here you will find multiple online resources such as our wiki page, several blog posts, and links to the repository sites. Our forum is also located on anyscript.org, and here you can ask questions and get help from some fellow Anybody users. I would also like to mention a couple of upcoming events. We have a webcast by Dr. David Lund from Leeds Beckett University next month. He will be talking about their mocap dataset of total hip replacement patients. Anybody technology will also be present at the World Congress of Biomechanics in Canada in July. You're very welcome to visit us if you're going to be there. To end this presentation, I'd like to mention that we maintain a publication list of papers using Anybody Modeling System and a library of previous webcasts. These are great resources if you want to get inspiration on how to use Anybody. This brings us to the Q&A session, and we will read some of the questions from the audience.